Okay. Hello, everyone. How did the practice problem go? Did you guys try them?
Can you try two?
Go ahead. What?
2B.
2B, that's the practice?
Yes.
Okay, we're gonna go through that. Great. So if you guys have other questions, put them on chat. I'm gonna say 2 words, I mean, not 2 words, but a little bit about the homework. You guys have, please read the feedback I write for you. If you don't understand them, which is of course very possible, let me know that you don't understand them so I can help you with them. Okay, and eventually I will put up the solution, but this takes a little bit of time. So the question that stood out in your homework are the following. So I usually address the problem that a lot of you had struggled with. So, and this is from the homework that I graded for you yesterday. And my question was, take the power set of this, intersect it with 1, 2. And I know that it was a little bit tricky, but that's okay. So what's the intersection is all the elements that are in this set and they are in this set. This is what the intersection is. So if we think about it, which elements are in this set? 1 and 2. Now the question, is the element 1 in the power set? No, because the power set is a collection of subsets. So 1 is not in the power set of 1, 2. How about, so remember when you're thinking about this is a set that has those 2 elements, 1 and 2. And then 2 is 2 an element of the power set. Again, no, because 2 is just 1 element, it's not a subset. So the intersection here is the empty set. There is no intersection between the 2 sets. Okay, please ask questions as I move on. Okay, so this problem stood out in your homework. Another one that actually kind of surprised me is the following. I gave you the set V, which consisted of 5 numbers. That's V. And the question is find V union the empty set. So it means everything which is here or here. But there is nothing here. So the union is nothing more than V itself. Okay, so because you have V and has object, you take everything in V and everything in the empty, but there is nothing in the empty set. So the intersection is V itself. So some student wrote empty 4, 5, 6. Why is this false? Why this is false? Who would like to pitch in? Why this is false?
I think it would only be true if it was V union the set of the empty set.
You're right, Simon. Simon, right?
Yes.
I mean, recognizing voices is hard. But you're right. But why this is false? Why this is false? How would I convince you that this is false?
Because the empty set is not an element, it's the set itself.
Right, because the empty set is not an element of the empty set. The empty set has nothing in it, has no element in it. So this empty set is not an element here. It's not an element of V, so it cannot be in the union. End of the story. To be in the union, it should be either here or here, but it's not here because there is nothing in here. It's just an empty box. You have an empty box, you take everything in this empty box, and then you take everything in 4, 5, 6, and you put them in the same box. But here there is nothing. There's only 4, 5, 6. End of the problem. Okay, so that was major issue, but so V union the empty, anything union the empty set is the anything, because the empty set there is nothing. If you want to take everything here, plug them in a box, but there is nothing here to put. So you're only left with those. And of course, after I followed this with V union, the set that consists of the empty set. Now the scenario here really changed a little bit. So now the union will have to be everything in V. So this is its contribution, and then everything in here. But in here now, the box is not empty. It has something in it. Whatever it is, it has something in it. Okay, so that should be the those two questions stood out. And a main idea is also the universal set. Universal set also is crucial. Universal set. You see, I cannot talk about complement without talking about universal set. The complement makes no sense without a universe. So suppose I say something simple. This student, so I'm thinking of all the student in my class. So all the student in MA348, that's my A. So what is a complement? It's a big problem. What's a complement? Every student not in MA348. Very good. Every student where? Is every student, every math major? Every student at PNW? Every student at whatever, in the world? What do I mean by complement? It means what is the universe I am talking to? And the complement will change with it. So if my universe are all math major at PNW, then a complement will be very clear. Every math major who is not in my class. If I take my universe to be all PNW student, then my complement will be every student of PNW. It doesn't have to be a math major. It can be philosophy major. It can be, I don't know, psychology major. It means all the psychology, all the students who are not in my class. This complement are very different from one another. Are you with me? So whenever there is a complement, it's what's not in here, but it's where. I need my universe. Where is it? And so whenever there is complement, we have to introduce the universe. Otherwise, complement make no sense whatsoever, because I have to tell you where I am. Okay? Now, why this showed up a lot? It showed up a lot when I asked you the following question. I told you to compare the complement of the intersection versus the complement of A intersect the complement of B. And I did tell you to draw the Venn diagram. In this case, the only way to draw a Venn diagram, and my question was, let A, B, and C be subset of a universal set U. You cannot sketch a complement, I repeat, without introducing a universe. So to be able to sketch that, you have to introduce a universe. You have to have an A, you have to have a B. And then the complement of the intersection, that's the intersection, the complement is this piece right there. Outside this is in my universe, but outside A intersect B. So that's the correct picture of the complement of the intersection. Right? So some students, I don't know what they did. They introduced A, B, and C, but it doesn't really make sense. We have a universe that we're working with. That's where complement makes sense. And this one, you guys now, I think you have the idea. This is your universe. This is A, and this is B. And you have to take a complement. So everything in a complement. Everything in a complement You have to intersect it with everything in B complement. So everything in B complement. So we're avoiding B. And we look at the region in common. And the region in common is, I will just put it in shadow. This will be the region in common. So that's what is going to be. That's it, the shaded region. Which is actually, if you look at it very carefully, what this is going to be. So definitely they are not the same, of course, but this is what, if you look at this Venn diagram carefully, who can give me a way to describe the shaded region? Beside this one, another way. Look at the shaded region. What's another way to write it out? Go ahead, unmute and tell me. We can find a formula for the shaded region, which is not this one. Actually, it's even easier. U minus, right, is the complement of the union. It's basically U, A union B, the complement of that, which is, as you guys are saying, exactly U minus A union B, which are the same thing. Okay, so that's the idea. So a lot of you did this mistake. That's why I had to emphasize complement. There is no complement without universe, because where are they? Not in here, but where? That's where the universe is coming to the picture. All right, and I think I'm almost done with the homework. The other thing is that there's a question about element of a set, element of the power set. You did fine, but it's edgy on the explanation. Some give beautiful explanation, I mean, definitely, but you guys were edgy. So I will just take the first question, part A, and let's get the answers very clear to that one. So, okay, I'll only do part A. And the question is, take this, all right? Is this an element of S? So the question, is it an element of S? Answer, is it an element of the power S? And I wanted you to justify. Okay. So the question, is it an element of S? And yeah, it's right there. It's one of those objects. So of course, it's an element of S. It's one of the objects S is made out of. There is no explanation except that it's one of those objects that S is made out of. But the explanation is for that. Is it an element of the power set? And remember, crucial. A set, let me call it set A. An element of the power set means it's a subset of S. So to show me that something is an element, you have to tell me that it is a subset. So who would like to finish? So the answer was yes. A lot of you got that. The explanation is not there. Okay, who would like to really explain it? So to show me, to convince me it's an element of the power set, you have to convince me that it's a subset of S. That's really what it is. So who would like to take off? Rachel, take it over. Rachel, you hear me?
Yeah, I'm here.
Yeah, go ahead. Explain it the way you explained it on your quiz. I think that was you.
Okay, let me see what I put for it.
You don't have to see. Think through that.
Because I used the word element in subset a lot, so I feel like it doesn't necessarily get to the point of why.
Okay, anybody else would like to tell me why? Remember, that's really what I'm looking for. To tell me yes, you have to convince me that, I'll write on the side what you have to convince me. You have to convince me that this is a subset of S. That's what it means. This is an element of the power set. It means it's a subset of S. I don't want you even to list the element of the power set. That's easy. So who would like to finish? Is this true? Is this a subset of S? Yes or no?
Would it be that
There's a
any
lot to talk
element,
about. What?
would it be that any element is a subset of a set?
Any element of the set, you mean?
Yes.
Yes. Okay, now let us connect things together. A is an element of S. True or false? I want to answer. If we're on the board, I will be talking at the board, but I can't. Is A an element of S? True. Hence, the set that consists of the element A is a subset of S. Is this logical? A is an element. It means the set that consists of that is a subset of S. That's the definition of a subset. If this is therefore, by the definition of the power set, that's what the definition of the power set, by the definition of power set, that's the kind of explanation I really would like you to do. By the definition of power set, A is an element of the power set. Okay, that's how I see that, you're really with me. So is this? Yes, because A by itself is an S. It means the set that consists of A is a subset of S, because everything here, which is A itself, is in here. Therefore, by definition of the power set, that's what the definition is. This is an element of the power set, because the power set is all those subsets connected. Okay. So some of you try to list the element of the power set, which is okay, but I actually want you to be able to think through it along those lines. All right? Okay. Any other questions about the homework? Okay, now I go to Chris's questions about the worksheet. So I try to give you like kind of a summary of what we did last time. And Chris, if my memory is right, I think it is somewhere number 2, right? Chris, help me out.
Yeah, 2B.
2B. All right. So what am I asking here in 2B? So I'm giving you 2 sets, A, that consists of 2 elements, B, 1 element. And I introduce 2 statements, 2 element of A, and Q, 2 element of B. And we say, of course, this is true, and this is false. All right, so that was my setting. Will you be upload the solutions to the practice problem worksheet? I'm planning to give some of them as a homework, Rachel. So it was your chance to ask me questions. So I will do 2 or 3 in front of you, and then the rest I'm going to assign them. All right, part A. And what I don't assign, I promise you to write them. Make sense? Okay. A, 2 is not an element of A. So the question is, express each statement in terms of P and Q and logical connective. It means and, or, not, if P then Q. So the first one is easy. 2 is not an element of A, or 2 is not an element of B. So I know that's not Chris's question. 2 is not element. Actually, let me write it here. 2 is not an element of A, or 2 not an element of B. 2 is not, or 2 is not. Quickly, how would you write this? Please, very quick.
P or Q.
What?
P or Q.
No, 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 no. Is not an element.
Oh, negation of P.
Right.
Or negation of Q.
Correct. Non-P or non-Q. All right? B. 2 is not an element of A union B. I want you to be very careful with that. First, write it. I don't know. Rewrite it so that we can really. rewrite it so that we can actually, first, let's try to express it in terms of P and Q. No, that's the question. I don't know. How can we rewrite it so we can really work with it?
Maybe 2 is not an element of A and B because it's combining the two together. Since it's a union.
Mm-hmm. So how can we break it up so whatever you say, you're not hesitant, you think? I'm really kind of breaking up to the bones. So whatever we write.
So when I say 2 is not an element of A and 2 is not an element of B.
You're right. You're right. I'm not even arguing that. How can I totally convince everybody that what you're saying is correct? Using the rule of logic, which is I'm not arguing with. 2 is not an element. It means, what am I negating? What am I negating? 2 is an element of A union B. True or false? Are you with me? 2 is not an element of A union B. It means I'm negating the fact that 2 is an element. So 2 is not. That's the negation. Okay. Why this will be helpful? It means, what am I negating? 2 element of A, or that's what means in the A union B, or 2 element of B. Am I right? Now I can do a lot of mistakes. Okay, so what am I negating? 2 element of A, P. 2 element of B, it's Q. And that's what your classmate actually told us. It means I'm negating P or Q, but what does De Morgan's law tells me? Non-P and non-Q. What does it mean? Now let's write in English. It means 2 is not an element of A, and that's going to be a very important fact, actually. If it's not an element of A union B, it means it's not an element of A and not an element of B. So the way it cannot be an element of the union, it means it's in neither one of them, which makes sense. Okay, so this way we broke it totally apart. All right. Chris, did it make sense?
Yes.
Okay, makes sense a little bit. All right, so okay, so C and D, I wanted to follow along the same route. It's not an element of an intersect B. It means you're negating the fact that it is an element, and then follow, and you're gonna get in more. I will do one more, and then I will, I will assign some as homework. As I said, they will be part of your homework, and what I do not assign as a homework will definitely, I will write it up for you. I decided to pick one. I don't care which one. And I mean, I picked D, but I don't think D is more important than the others. And let us write the following: negation, contrapositive, and converse, so that we can review all those very carefully. So I'm going to do just part, D as, so the question is, so if, that's an if-then statement. If, then X positive or X less than -1. And I tell you, assume X is a known number. And don't worry about its truth value. I mean, if you think a little bit, that's a true statement. So first, the negation. That's in if, then. If this, then that. All right. Who is ready for the negation? So first you have to remember, how do we negate a statement, an if a conditional statement? Yeah, its negation should be an and what and? You write neg, but let's be very clear. So let me write this a P, for example, and let me write this in R. R, Q, I don't really care. Okay, Q, because we're used to Q. So now I'm negating if P, then Q. And what's the negation? Nick will write it now in real logical format. It's in and of what? P and non-Q. Okay, so how can if then statement? Negation is how it can be false. It can be false if P is true and Q false. It means non-Q is true. So the way the negation should capture how your statement could be false. It could be false if in the situation where this is true and this false. P is true and non-Q is true. All right, so what's going to be the negation? Negation will be, there is no more if. X plus 1 is positive. So X times X. And how do you negate Q? Q involved an or in it. So the negation is going to be and X is negative and X is greater or equal to minus 1. So the negation is X times X plus 1 is positive and X is negative and X is less or equal to minus 1. Now, is the negation true or false? Is this possible? What can you say about the negation?
It's possible.
Is it true or false? Even if you don't know X. Read it.
Can be right.
Impossible. Why it can be right? Can this happen? What's this? And. What's this? And. Is it possible to have all three at the same time? Is it possible to have X negative? X bigger or equal to minus 1 means X plus 1 positive. So is it possible to have X negative, X plus 1 positive, and the product positive? No way. So the negation is actually false, whether you know X or not. Means the original statement is true. Okay, that's impossible to happen. You cannot have all those at the same time. You can't have X negative and X plus 1 positive and the product positive. If the product is positive, how can it happen? It means either both are positive or both are negative. So you cannot have one negative and the other one positive. All right, what's the contrapositive? Okay, remember, what's the contrapositive? Suppose I call them P or Q. The contrapositive is if non-Q, then non-P. Okay, and P, if P then Q and non-Q, those are logically equivalent. This is true, this has to be true. This is false, this has to be false. All right, so what's going to be the contrapositive? Remember, it's if, then. The contrapositive will be if X is negative and X bigger or equal to minus 1, then X times X plus 1 is positive. Now, is the contrapositive true? Is the contrapositive true? Yes, absolutely. If X is negative and X bigger than minus 1, which read X plus 1 is positive. So if X is negative and X plus 1 is positive, did I write something absolutely nonsense? My apology. non-P. If X is negative and X plus 1 positive, the product is going to be negative. The contrapositive is actually true, and it's actually easy to see that it's true than the original statement, because, I mean, it's very easy to see that it's true. So this is true, my original statement is true, my negation is false. Now, finally, the converse. Sorry, here I did a mistake if you guys are writing down. Logically equivalent, so we know true as well. Yeah, we know true as well, or we can think about it, yeah. But which one do you think is easier to show it's true? Nick, which one do you think is easier? The contrapositive or the statement? I mean, they are quite the original statement. Okay, I find this is very easy. Because if this is negative and this is bigger than -1, the product will have to be negative. Okay. Very good. They are the same. Converse. So converse is easy. The converse of if P then Q, if Q then P. So there is no negation. You just reverse everything. The converse may or may not be true. I'm not really going to worry about that. So it reads, if this all X less than -1, then X times X plus 1 is positive. And that would be my converse, all right? Okay. So this is like one of those problems. The rest should be fairly similar. As I said, some of them will be assigned to you as a homework. Everything I do not assign, you will have the solution clearly written on Blackboard. And if you have any questions in the meantime, like you're not sure of something, you just email me and I'll be glad to answer your questions. All right. Anything else? Any questions before I move on? Okay. So we keep practicing those logical statements. And then, of course, later on in the course, those are going to be crucial for us. But I'm trying to follow the book this time. And today we're moving to chapter 4. Okay. And counting. So we're going to do counting. Okay. So counting is just basically, I give you a list of objects. And you have to count how many objects are there in the list. So as simple as that. And so today we will do the easy part, and next time, get harder, but not very hard because most of you are basically have some ideas about this. So first, what's a list? Let's get that straight. A list, and I will keep it so you guys can write, but it's also in your book. A list of length n is an ordered sequence of n objects. And the word ordered is absolutely crucial. Ordered is very important. So when I say a list, is a sequence of n objects. So A, B, C, D is a list of length 4. 1, 2, 3, 4. Ordered means A, B, C, D is different from B, A, C, D. Okay? Also, A, B, C, D is different from that. Because when I'm putting bracket, what am I talking about? Because this mistake showed up also in your homework. The ordered pair is not. I'm talking about a set. All right, so in this case, I'm thinking of a set that have 4 elements. In this situation, the order doesn't matter. If I repeat the same letter a million times, it doesn't matter. So do not confuse ordered pair to this. So notation are crucial. But when I write this, I want you to understand the set. When I write this, I want you to understand it's just an ordered list of numbers. So that's really what a list of numbers. Now we're going to take a fairly simple example that we're going to work it together, but I needed to establish the first rule. All right, so here the problem. Example. In how many ways can we order a meal that consists of a sandwich, a drink, and a dessert at a restaurant? If the restaurant has 5 different sandwiches to choose from, 4 different drinks to choose from, and 2 different desserts to choose from. And you go and you want to order one of those, and one of those. How many possibilities you have? Of course, the sandwiches are different. So you have whatever, ham and cheese, you have whatever you guys like, different drinks, and 2 different desserts, and 1. So immediately I'm having answers. So I can think of my choice as a list very easily. The first object is the sandwich. And the second object is the drink. And the third object is the dessert. And the question is, in how many ways? And I'm seeing 40, but let us make sure we understand this 40 once and for all, okay? All right, so 40, absolutely. Let's see where this 40 coming from. Right. It's coming from 3 pictures, all right? So let us imagine the sandwiches. I'm gonna write them this way. So that's a sandwich. I have sandwich 1, and I have, right, we have 5. How many sandwiches? We have 5. So this is sandwich 2. You can name it what you want. 3, 4, and 5. So I have those sandwiches, 1, 2, 3, 4, 5. Let me get them a bit closer so they fit in one page. So 4 and 5. That's the sandwiches. Now, this is the thing. For every sandwich, I have the choice. So this is the 3 picture of 4 drinks. For every sandwich, I have 4 drinks. 4 drinks, and the picture goes on. So that's the 3. So this is now my list. I have 5 chances, 5 choices for the sandwich. Now, for each one of them, I have 1, 2, 3, 4 drinks. 1, 2, 3, 4 drinks. So between the sandwiches and the drink, I have 20 choices so far, which is 5 times 4. And for each one of them, and that's the 3 picture, I have 2 choices for the dessert. 2 choices for the dessert. 2 choices, 2 choices. And the choice does not depend, my choice for the dessert doesn't depend on the drink. So they don't tell you if you take a Coke, you have to pick chocolate chip. They don't really tell you that. So your choice is free. You can pick anything you want if you whenever for any drink. So for everyone, you have 2 choices, 2 choices, 2 choices, 2 choices. So you already have 20. And now for each one, 2 choices. So you're gonna have 20 times 2, which is 40 choices to pick from. So a lot of choices. That's why it takes us a lot of time to figure out what we want. So the idea is fairly simple. Of course, for every choice of sandwich, you have 4 for those. For each one of them, you have 2. So altogether, you're basically having the 4 for the sandwich, the 5 for the sandwich, the 4 for the drink, and the 2 for the dessert, giving you 40 choices. Right, this principle, this idea of multiplying, this has a name, and it's called the multiplication principle that you will be using continuously. So what does the multiplication principle tells me? Tells me the following. Suppose in making a list of links n, so in the way I thought about our drink problem or our food problem is as a list. The first object was the sandwich, the second the dessert, and the drink, and then the dessert. So that's how we thought about them. So, and you're making a list of links in. And there are A1 choices for the first. And A2 choices for the second entry. But here I added that. A2 choice for the second entry, regardless of what the choice was for the first. It means, regardless which sandwich I pick, I have 4 choices for the drink. There is no relationship between my second choice and my first choice in a way. And A3 choices for the third entry and so on. Then the total number of different lists is just the product. So You have list of objects. They don't have to be numbers, of course. They can be anything under the sun. So that's what you have. So here you have A1 choices, A2 choices, A3 choices. So how A4 choices and so on. So how many choices you have, it's the product. And this is called the multiplication principle for counting, which has occurred tremendously a lot. Okay. All right, so let's move to the first example. And please, if I am going fast, not fast, but I mean, if you guys cannot write, let me know. So read example number 1 and, tell me what the answer is. I'll give you a minute to do it because I don't think it requires more than that. Okay. So it's a license plate available. Each plate contains 3 letters. And the order matter because as you guys know, these are license plates. So I can think of every license plate as a list of 6 objects. And all right, who wanna give me the answers? Anybody? Chat, talk, anything. $26 times 26 times that, I agree, yeah. So I don't have a calculator, Nick, I'm sorry. I don't usually work with calculators a lot, unless I need them. So the first, each plate contains 3 letters followed. So this is the letters. I have 26 choices. 26. So you imagine this huge tree that I'm building in my mind. A 10, a 10, and a 10. Oh, sorry. Okay, so I will have 26 to the power 3. That's a multiplication rule, 10 to the power 3. Okay, and that's 3 depicts. That's my list, and that's how many. Let us say I make a very, very slight variation to the same problem, but now I require all the letters to be different. How will this affect our simple scenario?
You would have to do 26 times 25 times 24.
Absolutely, absolutely. We have no choice. So in this case, I have 26 for this, but now I don't have 26 choices. I have 25. I have 25, and the rest are 10, 10, and 10. So it's different. It's a little bit of variation. And the 20, no, my apology, that's 24 now. 24 times 10 to the power 3. Okay, so useful, but not hard. Okay, again, along the same lines, sorry. Yeah, I don't want to use factorials now. Okay. All right. Example 2. Again, consider list of length 4, this time, made with a ladder A, B, C, D, E, F, G. So 1, 2, 3, 4, 5, 6, 7 letters we have. All right, question number 8. How many such lists are possible if repetition is allowed? So length 4, so that's my length. That's my list. And how many are they? Repetition is allowed. 7 times 7 times 7 times 7. So I have 7 choices, 7 choices, 7 and 7. 7 to the power 4. Okay, quickly. How many if repetition is not allowed? Again, 7. I have a 6. I have a 5, and I have a 4. Or you can use factorial, but that's not really hard. Okay. Now what if I put one extra restriction on the problem? And I will tell you repetition not allowed, and the list has an E in it. And how many ways this could be done? So I'm not allowing repetition for a reason. I will allow it later on. But this time I want the list to have the letter E in it. How many possible cases this will happen? So you guys can draw any picture you want or any way you would like to do the problem. So it's again the same thing. List of 4 numbers. And we have 7 letters, but this time repetition not allowed, that's crucial. And I want the letter E in it. And the original list is, sorry, it's right there.
Since we already know one of the letters, wouldn't it be 6 times 5 times 4?
Okay, 6 times 5 times 4. That's your answer?
Yeah, I think so.
Okay. Can anybody comment? Can anybody comment?
Times 3.
Not the list has its own length 4, Peter. Anybody comment? So what your classmate is telling me, 6 by 5 by 4, because we know already one of them. So anybody would like to comment? What is your E? So we know that E has, I don't know, I don't want to talk. I want somebody to talk. It will be 6 times 5 times 4 times 1. The list would be, I'm still, okay.
Well, the E could be anywhere, right? It doesn't say like it has to be anywhere specific.
Right, how will this affect your answer? Okay. We have to split the problem in cases in a way. All right. I'm going to take the first cases where the E is here. Okay. E is here. How many choices I have now? 6 by 5 by 4. Correct? This is if you put your E here. What if you put your E here? Then you have 6 choices here. And here you have 5 choices. And here you have 4. So in this scenario, that's how many you have. In this scenario, that's how many you have. Am I right? So E can change its position. And when E is changing its position, the list is absolutely changing. Because repetition is not allowed. So if I pick any list from here where the E is positioned in the first entry, and any list from here where E is positioned in the second entry, there is no intersection between them. There is nothing in common. Okay, and now I can do the third scenario. So this, that. Now I will allow my E to be here. And now how many scenarios I have? 6 times 5 times 4. So I put 6 here. I have 5 for here, and I have 4 for here. So do you guys see the picture? And now I still have one place where I can put the E. I have to take, when I'm counting, I have to take every possible scenario on Earth. 6, 5, 3. So to this list, I also have 6 times 5 times 4. All right? So what's going to be, so what I did this time is that I broke my problem. So I'm looking for all the lists. So I broke them into 4 lists, which is basically disjoint. List 1, all those that have E positioned at the beginning. All those with E positioned in the second entry. All those with E positioned in the third. All those with E positioned in the fourth. So to be able to do that, I have to basically split my problem. So what's the total number of cases now? So the total number of cases, I'm sorry for the noise in the background, is 4 times 6 times 5 times 4. Okay, and somebody told me 840, and I trust the person. Okay, is it making sense? So we have really to take care, because the lists are ordered. So having E in the first spot is different than having E in the second spot. So I had to break up my problem into pieces. And question number 2, before I state my second rule, is if I take all the lists, I already said it, but I repeat it. If I take all the lists where E in the first entry, and all those where E is the second entry, is there anything in common between them? Is there a list which could be here and here at the same time? Yes or not? Can those have the same type of list? No, because the order matters. Absolutely. The order matters. Absolutely. The order matters. And E is in different position, and the letters are not repeated. And this will come later. Why I'm insisting repetition is important. But for now, they don't, because the letters also are not repeating. It means I cannot have an E in here. There is no way to have an E in here. Why I cannot have an E in here? Because there is no repetition, so I cannot have 2 E's. If there were repetition, I will have an issue. But because there is no, I cannot have E and E in here. E will have to be only in one spot. So those 2 are different. All right, this brings us to a second rule, so a second principle in counting. So we have the multiplication principle, which is we've been using. And there is another principle, very intuitive, called the addition principle, which is basically when I have a list like that, this type of questions. And the multiplication rule does not solve the whole problem. as you realize. Then I have to take my problem and split it into basically pieces. So I took all those that have E in the first, all those in the second, all those, and then I had to add the number of elements in each one of them. So this brings us up, or motivate intuitively, the second principle that we will call the addition principle. Okay, I'll write it and I'll explain it very clearly. Okay. So let's see what it said. If A and B, I'll state it for sets because that's how we're going to use it. Suppose A and B are two finite sets, meaning they have finitely many elements, such that the intersection is empty, and that's very important. It means they do not intersect. So this is A and B, this is A, this is B. There is nothing in common between them and B. So this is have, let us say, 5 elements, nothing intersection. This is have 3 elements. Then the cardinality, remember that this notation is about the cardinality. And the cardinality of A union B, so how many elements is there, is just how many elements in A plus how many elements in B. So that's called the addition principle. So as long as the intersection is empty, if I want to see how many we have in the union, how many in A and how many in B. And this generalizes. It means if I have a lot of sets, like, but such that no 2 of them intersect, okay, then also I can break up this. So it means I forgot to write it. So I mean the following. Suppose I have sets A1, A2 in general, AN. These are sets, finite, such that no 2 intersect. There is no intersection between them. No 2 intersect. Okay? Then the cardinality of the union is the sum of the cardinality. Okay. So this could be generalized too. But what matters is that they should not intersect. They are disjoint from one another. Now, however, if the intersection is not empty, then what's going to be the cardinality? So let us see the picture because I'm going to totally rely on the picture. So suppose I have 2 sets now. This is A and this is B. They intersect, so there are elements in common between them. So 1, 2, 3, 4, 5, and let us say there are 2 in common, and there are a bunch of terms here. And the question is, what is the cardinality of the union? How many we have? All right, again, I'll do it intuitively. How many in the union? It's everything in A. So everything in A. So you're counting 1, 2, 3, 4, and you're counting those 2. You add to it everything in B, but then you're counting 1, 2, 3, 4, and you're counting this again. But by doing this, you're counting the intersection twice. So then you have to take away the cardinality of the intersection. Okay? Right, so if you have 2 sets, if they don't intersect, cardinality of the sum is, cardinality of the union is the sum of the cardinality. If they do intersect, then the problem becomes definitely different. Then you have to take the cardinality of the intersection because you're counting it twice. Now, the addition principle is very useful when you have to count things, but to be able to count them correctly, you realize that, I have to break them into 2 sets. I count what's in this set, then I count what's in another set. And that's what we did in the previous problem. What we did in the previous problem, you don't have to write, but let me explain to you what we did in the previous problem. We had to count all the list with E in it. So the way we did it, we actually created a bunch of sets. So I'm going to call, let's see, E1, all the list with E in the first entry. And then E2, so that's really what was in the back of my mind. All the list E in the second entry. E3, all the list, third entry. And E4, all the list in the fourth entry. Okay? And this is my whole list. That's really everything, everything. And then I start thinking. First, everything in A, so A is actually the union. What do I mean by the union? Means everything in A has to be in one of those. There is no way out. Every list has 4 entries. So the E has to be either in the first, the second, the third, and the fourth. So I really broke my A into simpler set. Simpler, much simpler. And then I asked myself, can they intersect? And I've asked you that several times, and you told me no, rightfully so, because it's ordered. So having E in the first, having E in the second really matters. So by the addition principle, which was very intuitive, we said that the cardinality is the cardinality of the sum. And that's really the addition principle. So it's the idea of really breaking things into, taking a huge list and start breaking the problem into easier subset to do it. And then here we got, since they all had the same cardinality, we got the answer. That's really what we did in the previous problem. Yeah. So let us do our last problem today along the same line. Example. So you guys read it. So we roll a dice 4 times and record the result as a list of 4 numbers. So you take the dice and you actually roll it, and list of 4 numbers, 1, 2, 3, 4. So you roll it the first time, you get something, you plug it here, then you roll it, then you roll it, and you got here. What's the total number of outcome? Very quickly. Okay, 6 times 6, because we have 6, 6, 6, 6. So that's 6 to the power 4, absolutely the multiplication rule. Okay. So that's 6, that's 6, that's 6. Question number B, find the total number of outcomes that have exactly 1, 2. So of all those outcomes, how many have only 1, 2 in them? Fairly similar to what I did a minute before. Okay. I don't quite understand, Logan, your answer. Okay. Think through the problem. Always break the problem. Try to understand. So what is it I am looking at? So what am I looking at? I want exactly 1, 2. So I still have a list. 1, 2, 3, 4, all of them. And I want exactly 1, 2 in each one of them. total outcome minus, yeah. Anybody else? I will use that later on. I want you to think about it as, break it apart into little pieces.
Can you scoot the paper down a little so I can see what the conditions were? Thank you.
This one? Yeah.
Yes.
So exactly 1, 2. Okay. So I want exactly 1, 2. Anyone? 1 over, I don't, why 1 over 6? Where are you getting 1 over 6 from? Right, I know that. Yes. Okay, bring it back. We still have 5 minutes. Okay, anybody? I want exactly 1, 2. Again, I want you to break the problem. If you have, can I pick somebody?
Are we saying that there's going to be 4 different lists and each list has to have 1, 2? Or 1 out of the 4 lists has to have 1, 2?
All the list, everything that have exactly 1, 2. So that's the scenario. So you roll the dice and there are 6 to the power 4 outcome, right? But those are every possible outcome. So I can have like 4 the first time, I can have 3, I can have 2, I can have 1, right? And so let us fully understand, because you're not answering me, it means you guys are not understanding my question. So I'm rolling the dice, and there are several options. So I can have like 4, I can have 4, I can have 3, and I can have 2, right? Or I can have 2 and 2 and 4 and 6. So I have a lot of outcomes. Which ones I am interested in? I'm interested in those that have 1, 2. So I'm interested in this type of outcome. I am not interested in this type of outcome. So my question is, how many have only 1, 2 in them? It means it means that only once the dice, when we roll it, gave me the number 2. Rachel, did you understand?
I think so. So would it be hold on, I had it, I thought.
So we're rolling the dice, and the first roll, I put what I got, the second time, the third time, and the fourth time. My question is, of all those outcomes, how many of them only you get 1, 2 when you roll it? You could have gotten in the first attempt, the second attempt, the third attempt, the fourth attempt. I don't know, but one of them, only one, is it 2?
Would 3 out of the options have to be 5, and then the option that could be 2 have 6? Or am I way off?
Yes, Nick, yeah, that's okay. Don't, I know. Let us bring scenario. Give me the scenario to understand my scenario. Give me a scenario where my questions apply. So this is a scenario that satisfies 1, that I got 2 only once. Another scenario. That's my scenario. That's another possibilities. Okay, because I care about the order in which I am really getting those numbers. Okay, a third scenario. So these are the scenario I'm interested in. The last scenario, I can put 2, I can put 6, 6, 5. Okay, because I am putting, when I'm rolling, I'm putting my outcome as an ordered list. So how many possible cases I have now? Yes, Nick, let us answer this question. And your question is coming next time. It was planning to come today, but it's going to come next time. Okay. So, scenario 1 is that the 2 came at the last roll. And how many possibilities this can come? How many possibilities we have for that? Anyone? Why you guys are confused? What?
Would it be 5 because it can't be? We can't use 2.
Right. How many we have for that?
It would be 5 again, right?
Yes, there is no other choice.
All right. Well, I stepped away before you asked the question, so I wasn't really sure what the question was.
Yeah, I noticed that. That's why I repeated the picture. All right. So it means we have 5 to the power 3 in this particular scenario. In this scenario, my 2 now is here, the first time we roll it. How many cases here? 5, 5, 5. So what I care about the order in which the rolling happened, okay? And exactly 5, 5, 5, and 5, 5, 5. So again, I am basically breaking my problem into easier problem. Those where the 2 was rolled last, the 2, because of my example, rolls the second, the rule 2 rolled at this stage, and here the 2 rolled at that stage. So what we're going to have is 4 times 5 to the power 3. Okay. That's the total number. And exactly 112 is absolutely, again, important here, because if I want more than 12, it's the next question. Right? Okay. I definitely would like to stop here, and I'm going to assign some practice problem from the book itself and do them for next time. If you have questions, we will discuss them in class, and if you don't, I will move on. All right, any questions for me? Usually this class, unfortunately, I have to leave quickly because I have another class right after you. But do you have any question before I let go? Anyone? Okay, so I'm gonna just assign practice for Wednesday, not a lot of them, just, you know, try them, and see you on Wednesday. All right, bye-bye, guys.